Good morning, everyone. Welcome. In today's lecture, we're going to do something really important. We're going to build a bridge from the theoretical world of algebra, X's and Y's, to the very practical, high-stakes world of business and finance. Specifically, we'll be looking at how we can use quadratic functions to tackle one of the most critical questions any business faces: how to maximize profit. Now, I want to be clear, what we're about to cover isn't just a textbook exercise. It's a fundamental tool, a way of thinking that you'll be expected to use in your future careers, whether you're a manager, an analyst, or an entrepreneur. So let's get started.
Okay, I want you to put yourselves in this scenario. You're on the senior management team, your company is about to launch an exciting new product. The engineers have done their job, the marketing team has a campaign ready to go, and now all eyes are on you for the final crucial decision: the price. Now think about this. If you set that price too high, your customers might just walk away. You'll be left with a warehouse full of products nobody's buying. On the other hand, if you set the price too low, you might sell a ton of them, but your profit on each one is so tiny that you don't even cover your costs, and you end up losing money. It's a classic dilemma, right? Well, our goal today is to replace that guesswork, that gut feeling, with a solid mathematical method for finding that perfect sweet spot.
For a long time, pricing decisions were, less scientific. Companies would look at what their competitors were charging, maybe run a few small market tests, or honestly just trust the instincts of a seasoned executive. And look, there's a place for that experience, but those methods are loaded with uncertainty. In today's business world, we can do so much better. We use a powerful tool called a mathematical model. Think of a model as, it's a set of equations that acts like a financial simulator for our business. We can plug in our data, what it costs us to make the product, what our market research tells us about how many we can sell at different prices, and we can build a function, an equation that actually describes our profit. This lets us test out every single possibility on paper without risking a single dollar in the real world.
Now let's be really precise about our goal here. Sure, any price that brings in more money than it costs is technically profitable, but that's not good enough, is it? We're not aiming for some profit, we're aiming for the most profit possible. The name for this discipline is optimization. Optimization is just the process of finding the absolute maximum, or sometimes the minimum, value of a function. In our case, the function we care about, the one we want to get to its highest possible point, is the profit function. We are on a hunt for the one single production level that gives us the absolute peak of our financial performance.
So how do we actually build this profit model? Where does it come from? Well, it's built from three fundamental building blocks, three key functions that are really the bedrock of managerial economics. We have the revenue function, the cost function, and then the one we get from combining them, the profit function. It's absolutely essential that we understand each of these pieces first before we can put them all together. So let's break them down one by one.
First up, let's talk about the revenue function, which we'll call R of X. Revenue is pretty simple on the surface, right? It's just the price you sell each item for times the number of items you sell. Let's call the number of items X. Now, you might think this is just a straight line. The more you sell, the more money you make. But it ignores a key rule of economics, the price-demand relationship. Think about it. In almost every market, as you lower the price of a product, what happens? More people want to buy it. Demand goes up. This relationship can often be modeled by a straight line with a negative slope. Now, here's the key part. Remember, revenue is price times quantity. So if our price is determined by a linear function, say P of X equals mx plus b, our revenue, R of X, becomes mx plus b times x. And when you multiply that out, what do you get? R of X equals mx squared plus bx. See that x squared term? That's what makes our revenue function a quadratic. And because the m, the slope of our price-demand line, is negative, it's a parabola that opens downward. This shape perfectly captures that real-world dynamic where cutting your price at first boosts revenue, but if you cut it too much, your total revenue actually starts to fall.
Next, let's look at the cost function, C of X. This models all the money we have to spend to produce our items. For a lot of business models, we can keep this pretty simple and assume it's a linear function. And that makes sense because costs usually fall into two main buckets. First, you have fixed costs. These are the things you have to pay for no matter what, even if you don't produce a single item. Think about the rent for your factory, insurance, the salaries of your office staff. In a linear function, C of X equals mx plus b, the fixed costs are that y-intercept, the b. Then you have variable costs. These are the costs tied directly to production. The raw materials, the wages for the workers on the assembly line, the power for the machines. For every unit X you produce, these costs go up. This is the slope of our line, m. So our total cost function is just a straightforward line that adds those two parts together.
And that brings us to the most important one of all, the profit function, P of X. This is the bottom line. It's what we're all here for. This function represents our net earnings, the money we actually get to keep. It's not just about how much money comes in or how much goes out, but about that crucial difference between the two. This is the number that creates value for shareholders and allows a business to grow.
The relationship between these three functions couldn't be simpler, but it is absolutely fundamental. The profit function is what you get when you subtract the total cost function from the total revenue function. P of x equals R of x minus C of x. This simple equation, this is the heart of our entire model. By doing this one piece of algebra, subtracting one function from the other, we're going to create a brand new function, our profit function. And that's the one we can finally analyze to find our maximum value.
Okay, so we've built the model, we have all the component parts. Now for the fun part, using it to find the solution. Our goal is to find that specific number of units, that specific x, where our profit function, P of x, hits its absolute highest point. Now, in the language of algebra and geometry, what do we call the peak of a parabola? We call it the vertex. So our big, complicated business problem has now boiled down to one single mathematical task. Find the coordinates of that vertex.
Let's look under the hood for a second at the algebra. We said our revenue function, R of x, is a quadratic that looks something like negative ax squared plus bx. And we said our cost function, C of x, is a line, something like mx plus d. So what happens when we do the subtraction? P of x equals R of x minus C of x. We get P of x equals negative ax squared plus bx minus mx plus d. If we distribute that negative sign, we have P of x equals negative ax squared plus bx minus mx minus d. And we can just group those middle terms together to get P of x equals negative ax squared plus b minus mx minus d. Now look closely at that result. Is it still a quadratic? Yes, the highest power of x is still 2. And what about the very first term, the one that determines the shape? It's still negative ax squared, it's still negative. So our profit function is also a downward-facing parabola. This is such a critical result.
So what does that mean for us? Well, this mathematical property is what makes this whole problem solvable. The fact that our profit function is a downward-facing parabola guarantees that there is one and only one maximum value. There's a single peak. This means there is one perfect production level that will give us the most profit, and any other number, whether it's higher or lower, will give us less profit. Our complex business decision has been simplified to finding that one specific point, the vertex of our parabola.
This chart here gives you a really intuitive way to picture what's going on. Think about it. If you produce too little, over on the left, your revenue isn't even high enough to cover your big fixed costs, like rent, so your profit is low. As you make more, your profit starts to climb. But if you go too far, over to the right, you've flooded the market. To sell all those extra units, you have to start slashing your prices, and that just destroys your profit margin. That tall bar in the middle, that's our vertex. That's the sweet spot, where we've perfectly balanced everything to get the absolute peak profit.
So, how do we find that sweet spot without just guessing? Thankfully, there's a formula. For any quadratic function that's in the standard form, ax squared plus bx plus c, the x-coordinate of its vertex is always found with this little formula. X equals negative b divided by 2a. All this formula really does is find the center line of the parabola, its axis of symmetry. And since the vertex is the highest point, it has to be right on that center line. The a and b in this formula, those are just the coefficients from our profit function that we figured out a minute ago. This formula is going to give us the exact number of units we need to produce.
This brings us to a simple, repeatable, three-step game plan for solving these problems. Step 1, you take your final profit function, P of x equals ax squared plus bx plus c, and you correctly identify your a and b coefficients. Step 2, you plug those numbers into the vertex formula. X equals negative b over 2a, and you solve for x. This number x is your golden ticket. It's the optimal number of units to produce. But you're not done. Step 3 is absolutely crucial, and it's where a lot of people slip up. You have to take that x value you just found and plug it back into the original profit function. That will finally tell you what your maximum profit actually is. So the x-coordinate tells you how many to make, and the y-coordinate tells you how much money you'll make.
So let's imagine we've gone through step 2. We've done the calculation, and our formula spits out the number x equals 1,000. What is this number? What is its business meaning? Well, this is our optimal production quantity. Our model is telling us that the way to get to the very top of that profit curve is to produce and sell exactly 1,000 units. This now becomes our target for the entire operation.
And now for step 3, we take that number, x equals 1,000, and we plug it back into our profit function, P of x. Let's say we do the math, and the answer is P of 1,000 equals $90,000. This is the y-coordinate of our vertex. This is the grand prize. It represents the absolute maximum profit we can achieve. Our model is telling us that if we produce 999 units, or if we produce 1,001 units, our profit will be less than $90,000. This is the financial peak we've been searching for.
All right, we've completed the math. The quantitative analysis is done. But, and this is a big but, in the real world, just having the numbers isn't enough. The most critical skill for you to learn is how to translate these mathematical results into a clear, confident, and actionable business recommendation. This is the step that takes you from being an analyst to being a decision maker.
I mean, think about how you would present this. In my class, you might be tempted to just write down, the vertex is at x equals 1,000. In the professional world, that's not going to fly. Your job is to translate. You'd walk into that boardroom and say something like this. Good morning. Based on our financial modeling, the analysis indicates that the profit-maximizing output for our new product is 1,000 units. At this level, we project a maximum profit of $90,000. Therefore, my recommendation is that we set a production target of 1,000 units and align our sales and marketing efforts to move that exact volume. See the difference? One is a math answer, the other is a business strategy backed by data.
Now, before we finish, I want to be crystal clear about two very common, very critical mistakes. I see them all the time. First, students will get the answer x equals 1,000 and think that's the optimal price. That's wrong. Remember, in our model, x always represents the quantity of units. The vertex formula tells you how many to make. If you wanted to find the best price, you'd have to take that quantity, 1,000, and plug it back into your original price-demand equation. The second mistake is that people will calculate x equals negative b over 2a and then report that number as the maximum profit. Again, that's incorrect. X is the input, the quantity. The profit is the output, p of x. You have to finish step 3 to find the actual dollar amount. Getting these two things straight is absolutely essential.
So let's just zoom out and recap why this whole process matters so much. What we've really done today is we've replaced subjective guessing with a data-driven strategy. This gives everyone in the company, from the factory floor to the sales team, a clear, unambiguous target to shoot for. In a tough market, the companies that can accurately model and optimize their business like this are the ones that win. And finally, the ideas we've used here, finding the maximum of a function, they're the foundation for much more powerful models you'll encounter later in your careers, in everything from supply chain logistics to financial engineering.
So I'll leave you with a final question to think about. Today, we used a pretty simple shape, a parabola, to solve one of the most fundamental problems in business. Just imagine what else is possible as you learn more advanced mathematical tools. How could you model the perfect inventory level to minimize storage costs but avoid stockouts? How could you find the most efficient delivery routes for a fleet of trucks? How would you allocate a marketing budget across 5 different social media platforms to get the maximum impact? The reality is, almost every big business challenge is, at its core, just an optimization problem waiting for you to build the right model to solve it.